is in your fifth unit is multi-rate digital signal processing. In short, the people call it as MDSP, multi-rate digital signal processing. And the second one is finite word length effects. These are the two subtopics under your fifth chapter. So in the first half, we are going to say what do you mean by MDSP, why to go for MDSP, and what are the topics under this. The topics which the important topics. I can in all we can if you see your syllabus content, you can see there are a lot many topics. But if you from examination point of view, there are hardly 2 to 3 topics which are uh, quite important from the examination point of view, and they are is your the first in the first half of the fifth unit they will be asking on your decimation, interpolation, or I by D, interpolation, divide by decimation. These are three important topics, easiest topics which they can ask directly. You have to write little bit derivations, total derivations, and rest all theory. In the second half we are going to study about finite word length effects. Means earlier, what are the fourth unit where you studied like you have first taking the signal, doing the system analysis, which system is better, how to do find the response of different systems, what are the mathematical tools you used, all this blah blah, that means completely digitalizing of a signal, the advantage of digitalizing a signal, that all you will talk about in case of your first 4 units. In the last 4 15 you will say, though you are using your digital filter, but definitely it will suffer from some drawbacks, it is having some drawbacks. So those drawbacks are, as it is a finite, digitalized, we are dealing with a finite number of sequences. So definitely you will have a limited uh, kind of thing. So therefore, we study about finite word length effect, and in that under that finite word length effect also there are a direct problem without changing any value also, which they will ask is your find out the limit cycle of oscillations and the deadband. One problem will be there directly from that. So and it is easy to understand, easy to solve even, which we study in the next classes. So, in short, put together, I can say, in first part, you study about interpolation, decimations, and I by D. Third, we is talking about the theory about what are the different types of errors which we come across when we are dealing with the dealing
Okay,
signals.
ma'am.
Uh,
Ma'am, it is not clear, ma'am.
it is not clear.
Yes, ma'am. Audio, ma'am. Some disturbance is coming and volume is also less, ma'am.
Volume is also less. Okay, I will. I'll talk loudly. Hello. Is it okay now?
Yes,
Yes,
ma'am.
ma'am.
Okay, so
Yeah.
till now what are the bug identity gone all?
No, ma'am. It is there, ma'am.
Okay, fine. Bug. Okay.
Not bug, ma'am. MDS.
Okay. Understood.
We listen, ma'am, but it's not clear.
You want me to repeat again? No, na?
No need, ma'am.
No, ma'am. No, ma'am.
No,
Continue, ma'am.
ma'am.
Okay. In one two lines only I'll say. Earlier I was discussing about the first 4 units in which you suffer with some digital. You will enjoy the digital benefits. In the fifth unit, you will talk about the drawbacks of digital. In the second half of the fifth unit, in case of first part of your fifth unit, that is multi-rate DSP, second part is your finite word length effects. In that, this is a very theory topic, easy to understand, easy to score. One problem will come from limit cycle oscillations and deadband, and another theory kind of thing they will be asking from the MDSP, multi-rate digital signal processing. Okay, so now, so this rest things we'll see later. Now let us start with your multi-rate digital signal processing. Actually, this is one of the subject of your MTech, not in your BTech. So that's why they very precisely, very briefly, they are explaining you what is what in your syllabus itself. Okay, so let me tell you that we know that there are not many advantages of DSP. Not many advantages of DSP means you can see what is the practical application of DSP. One can say, am I audible now?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So I can what I can. Who is that? Whose sound? Okay. So what I was saying. Huh. One can say what are the advantages of digital signal processing. The phone, the mobile phone which you use, that is the best example of your DSP. I can say. How I can say, because we know that we are doing we can see different types of ringtones, voice encoding, speech encoding, your text messages, whatnot. Whatever the applications you are finding in your mobile phone, they all comes under the they are all the applications of digital signal processing only. So now, what is the difference between your multi-rate digital signal processing and the normal digital signal processing? So definitely, multi-rate DSP is come from your digital signal processing only. So what is the meaning of this multi-rate? Multi-rate. We can say there are different sampling rate which we are talking about. Multi, many, sampling rate. Only sample, but they have 8, they made it multi-rate, but actually that is nothing but different sampling rate when we are dealing. That means how you'll understand that. What is that? Multi-rate digital signal processing is when you are dealing with a system which operates on the different sampling rate, that is called as multi-rate digital signal processing. When you have different sampling rates from your input to output, we call it as multi-rate digital signal processing. People also define like when we are converting one sampling rate to another sampling rate, and the system which employs this, which does this function, that is called as multi-rate digital signal processors. Okay, now what is that means definitely you would not understand what is that sampling rate and what I'm converting and why this conversion and all. So you can take the example of, like, you know that what in case of telecommunications, the application which you can find is you are dealing with telephony signals, and let us say you are dealing with your compact disc. Both of them operates at different sampling rate. Means we can see that we know that here, let us say I'm talking about, here is your one input which is discrete in time, discrete input we are giving to x of n, and the discrete system which we are giving the input to, and from that definitely the output which will be obtained also discrete in time only. So I can rewrite this like x of n, nothing but x of n into tx. Means here I'm talking about the sampling rate of the input which we are giving. So input sampling rate, and this y of n is the output sampling rate. When this input sampling rate and the output sampling rate, they are same, means you are talking about the two devices which uses the same amount of frequency, same amount of band they operate in. So that time we say your Tx equals to Ty. At that time you need not to go for multi-rate digital signal processing, because both the inputs as well as output, they operate on the same band, same sampling rate they are going through. Therefore, when Tx equals to Ty, we say that that is normal DSP, it is not multi-rate DSP. So you need not to go for this topic. But when you are saying that your input and output sampling rates, they are different. When Tx is not equal to Ty, that time definitely we have to go for conversion of one sampling rate to the another one, and who does all this, that is nothing but your MDSPs. Okay, now here what example I was giving is, here your telephone signal which operates at a sampling rate of 8 kilohertz, and your compact disc which is having the range of 44.1 kilohertz. So when you are sending this data through your telephone lines, you can see this is the input which is at this frequency band, and this is what on which we have to send the data. Means I can say your system is now your channel, communication channel, through which you are sending the CD data, compact disk. You want to store the data on compact disk. You want to transmit the audio signals. You want to transmit the music signals using all this one system only, using through same channel only. At that time, the music channel, the audio signal, the compact disc signals, they are all of different. They operate on different sampling rate, but you want to pass them through through a common channel which is having some sampling rate. So obviously there is a need of conversion of this sampling rate from one sampling rate to the another one. That is what your MDSP is. So widely in telecommunications, MDSP plays a very important role to convert from one sampling rate to the another sampling rate, so that the data can be easily transferred through the medium. Okay, that was a practical example. So what are the steps to convert the sampling rate from 1 to 10k? One to other means what I am saying, that my way of presenting, or my way of I can say, when I'm transmitting a signal which is having a sampling rate of 8 kilohertz, and other people are transmitting their signal at 12 kilohertz or 16 kilohertz. That means now these two sampling rates differs from each other, right? They should be, and they have to transmit through one channel only. So that time, definitely, if that channel is of 24 of kilohertz which operates on that, so definitely I should do something so that this 8k will get converted into 24k, this 16k also will get converted into 24k. So what are the steps how to convert one sampling rate to the another? Is nothing but this can be achieved with the help of two conversion methods. That is, one is A by D converters and other is digital domain converters. A by D converters and digital domain. So what happens in A by D converters, that we have to see first. Okay. Uh, A by D converters. Here, definitely we are dealing with the input signal, which is discrete in time, means digital signal we are talking about. You can see that there is a representation which I have drawn over here. That is, at n equals to 0, some value, at 1, some value, 2, 3, 4. Some values are existing at different intervals of time. That means you are sampling the input at the rate fx, nothing but 1 by tx. Now that you are going to give to the D by A converters. That means what? You are having a digital signal, you are converting into an analog signal, and because this is one of the way how one can convert from one sampling rate to another. It is same like Nyquist criteria, the sampling process of analog signal which you have studied in your analog communication subject. It is same like that. What you do for that? You will take when you do perform sampling, or you can say when you are converting an analog signal into digital, what you do? First you take analog signal, then you sample it, then quantize it, and then decode it. That's how you get your analog to digital signal. So here what they are doing over here, you are having a digital signal with you. Instead of doing something on your digital signal, first they are interested to convert that digital signal into analog signal. In LICA you studied what are the different types of D by A converters, right? So using those D by A converters, you are getting some kind of envelope of this, then some kind of analog signals envelope is this, because your input is this discrete in time. Now you get a continuous time signal over here after conversion of digital to analog. Once you have done this, means now this is what the input of your sampler. So first thing, you have given some input, you have converted this, you got different sampling rate. Now with this different sampling rate, again you are going to sample, like how you have done in your A to D converters. You have sampled your analog signal. That means now this is what your signal is, which will be acting as an input for this, and from that you will get another sampling rate. This is how you can convert one sampling rate to the other sampling rate. Okay, that means here you can see I am taking first D by converter is a big task actually, if you remember your LICA subject, right? Second way, again your AC here, analog communication subject. In both the things you can see there are lot of approximations we are doing when we are converting one signal to another form, discrete time signal to analog, then analog of one sample again to do the sampling. That means to achieve the two different sampling rates, we have to take lot of trouble, and in this troubling also we can see that there is a loss of data. There will be a huge amount of loss of data will be there when you are doing A by D converters domain or method, because here when you are doing this we are doing approximations, again when you are doing this again you are doing lot many approximations, and these approximations are in cascade. So definitely we know that when in this systems, when you are doing cascading means you are doing multiplication, right? So when that means your multiplication value will be quite larger than your addition. So put together you will have a huge amount of loss of data when you are going to have this method of A by D converters. A by D converters. So then when I'm counting all the disadvantages, then why I have to prefer for this A by D converter? because here I'll be least bothered about your fx and fy value. I don't find any kind of relationship between fx and fy. I will always saying that fx and fy will be any arbitrary value, any arbitrary value which need not to be same, which need not to be same, which need not to be equal, or which need not to be having any kind of relationship between each other. They'll be quite independent. That is the only advantages when one is opting for A by D converters to have conversion of sampling rate from one sample to the another sample. Okay, so this advantage is what? A loss of data and definitely a loss of quality. That is because of approximation which we are doing. So that's why we have to go for one more topic called as digital domain. In digital domain, definitely unlike in your A by D converters where I was first taking met because I am dealing with DSP. DSP nothing but your digital systems, digital signals. In digital signals, here they have converted your digital to analog and then sampled again, then got some different sampling rate. Here in case of digital domain, purely I'm not at all interested to convert again D by A, simply as it is that X of n I will be taking, which is sampled, which is the input sampled at a rate of fx is equals to 1 by tx. Then I'm giving some kind of system. The system is also discrete in time systems, and the output is again discretized. That means I'm not at all going to convert D to A or A to D again. Simply a discrete input, a discrete output. The system I should use, that system should work in a such a way that which accepts this, which converts the one sampling rate into the another sampling rate with some sort of relationship. So means in these two, if I compare, I can see your fx or fy may be any arbitrary value. They need not to have any kind of relationship with each other. That means fx is greater than fy, f or vice versa, or anything. We are least bothered. Any arbitrary value we are able to take free. But here in this case, when you are going to digital domain, as you are not doing much approximations, that's why what we'll be doing is we'll be concentrating more on the relationship between fx and fy. Will be some of something of sort. What is that? Maybe your fx is greater than fy, your fy is greater than fx, anything. It will be anything. So some sort of relationship we have to maintain. The system should work on a principle that the fx and fy, they are not any arbitrary values. They are having some sort of relationship between each other, and they should be able to convert the sampling rate from one to another. That means what? Your fx will, fx is input sampling rate, your fy is the output sampling rate, and both of them are have to maintain a some constant value. Now, so as we are talking about digital domain and there are no approximations, no loss of data, so definitely in your subject or when multi-rate DSP processors engineers definitely choose a digital domain, not by A by D converter. So this is only for your good to know information. If there is, apart from digital domain, you will be having something else also. If you are not bothered about the loss of data, you can choose this one also, which is a little bit tedious. That's it. But now here, this in our subject, we have to study about this digital domain because I did not say anything about this system. I said this is the one system which accepts some discrete input time signal and which converts to the discrete output time signal. Because as the system is also discrete and it has to maintain some relationship between your output sampling rate and input sampling rate. So, so that's what I said. But I don't know what type of systems I'm using and what I will do in that. So for to study that, that only we have to see. Next is this what this system, what that system is, which convert my sampling rate from one form to the another one form into the another one. Okay, so that is nothing but up sampling and down sampling, up sampling and down sampling. This is the all these are almost a revision kind of your signals and systems which you might have remember. Okay, in digital domain, we can do sampling using upsampling and downsampling. Now, let us say I have taken one example wherein, because I said the must and should condition is what in case of digital domain, you should have some sort of relationship between your fx and fy. So let us say I am saying that my fy is greater than fx. My fy is greater than fx. That means I mean to say I have a fx, I have x of an input which is having sampling rate f of x is equals to 2 kilohertz, and my fy, my the the sampling rate which I want to convert is to 4 kilohertz. Is to 4 kilohertz. Means my fx is 2 kilohertz, my fy is 4 kilohertz. So I should have some relationship. From that I can understand my fy is greater than your fx. Okay, fy is greater than your fx. That means fy is twice times of your fx. This is what the relation I have. I want fy fy is 4 kilohertz, fx is 2 kilohertz. So I'm doing for upsampling. So definitely I'm writing this equation like fy into twice of fx. What is that? You see now. To make you understand this, I'm just taking one sequence, one example of discrete time sequences. Let x of n equals to 1, 2, 3, 4, and 1 is the origin of this. That means these are the magnitudes and these are the time instants, right? So till this only we'll be finding in our problem. X of n equals to 1, 2, 3, 4. That means what? When n equals to 0, it is 1. N equals to 1, it is 2. N equals to 2, it is 3, and so on. So if I draw the sequence over here, graphical representation, if I draw, I can say this 0, 1, 2, 3, and these are the magnitudes. Now here I want to have fy greater than your fx. That to how much? By 2fx. You can take any value over here I have taken 2fx. Okay, now here I can see this time duration, I'm calling it as sampling rate. This time duration I'm calling it as sampling rate. What is the sampling rate? The distance between two samples. The distance between two samples is a sampling rate represented as a tx. Okay, now here what I want is I want to upsample. Means I know that t equals to 1 by f, right? So now I'm choosing to increase my sampling rate. What I'm doing here, you see, what I'm doing here is I'm inserting some zeros. In my given sequence. I'm inserting some zeros in my sequence, and the zeros are added or inserted in a such a way that I will insert zeros by this rate. Means if I'm having here 5, that means 5 minus 1, 4 zeros I'm going to insert. If I'm having 3 minus 1, 2 zeros I have to add. Here I'm upsampling by 2. This is the symbol of upsampling. When I'm upsampling by the factor of 2, I'm saying that 2 minus 1 zeros I have to insert into it. Then only I will get a upsampling, I'm saying. Okay. Now let us say in general, people will call this as this common alphabet which is given to this is I, capital I. Okay. So now here you see what I heard, what I'm saying, that inserting zeros and all. I want this sampling rate to be reduced. I want this sampling rate to be reduced because t equals to 1 by f, right? When my t is reduced, your f will be more. So that's the reason. And as I want to do upsampling, I have to reduce the distance between two samples so that I can get the more frequencies over there. So how I will achieve that? By inserting zeros in between the two consecutive samples, two successive samples. Now how many zeros I'm going to insert? I'm saying I minus 1 zeros I'm going to insert. Now you can see when I'm inserting, let us say I'll start with n equals to 0 as it is. So I haven't inserted over here n equals to 0. Now in this between these two samples, just first what did I do? What are the samples I have noted as per my input given sequence? I drove it. Same thing I have extended. Now as I have to insert the zeros in between, what I have done is from this 0 to 1 sample, this sampling rate I have to reduce. I have inserted zeros over here, here, here. That means in between of two samples we have inserted. And now because of that, what you can see, your input here 0 to 1, that is 1 to 2 is the amplitude. Now here 0 to 1, you have one more sample which amplitude is 0 over here. Now you can see I'm not bothering about amplitude here, how much it is. Simply have inserted zeros over here. Why so? Because I want to reduce this time interval to this. That means I can say that I have reduced the sampling rate. That means new sampling rate is this much only. Earlier the sampling rate was this much. So from this what I understand, because of this what happened? At 0, magnitude is 1. Now at 1 the magnitude is 0, at 1 magnitude is 2, at the new samples you can see, the new sequence, new n values you can see of y of n, because this is what my x of n 1 2 3 4, when it started from n equals to 0 and ended at n equals to 3, started at n equals to 0, ended at n equals to 3. In case of y of n, in case of y of n, you have started your sequence from 0, same like this, same like this, but now the last sample it was at the interval of 3, right? But here if you see, the sample is arrived at the interval of 6. At n equals to 6 you got the last sample, because of adding zeros over there. So if I draw the sequence, if I write the sequence from this is 0 0 1 0 0 1 2 3 4 5 6. These are my new n intervals, new invert intervals, because of adding these zeros over here, because of inserted the zeros in between. So that means the magnitude, if I see the 1 at 0, the magnitude was 1, 0 the magnitude is 1. Which means what are the actual input data is there, it is coming as it is, it is coming as it is, only you have inserting zeros. It was at 1 it was 2, but here at yes, here at 1 it was 0, at 2 it is 2, again at 3 0, 4 3, 5 0 and 6 4. That means what you have done, you have got the magnitude, but that magnitude which occurs earlier at the sampling rate of 3, the same amplitude will occur at the sampling rate of 6. So that is what we are saying, we have done some kind of upsampling to it, because you have reduced the time interval, you got the frequency doubled, and that is what I wanted here. I have f of x something like this, I want fi which was twice of fx, and that I have done over here. So the standard representation of your upsampling is this fx, the fx or x of n, a discrete time input which is sampled at the rate of fx, is nothing but 1 by tx. When I have given to the I stands for interpolation here, actually I will not say about interpolation now, simply this is interpolator. So this is representation of upsampling interpolation. The output is sampled at the output y of n, which is sampled at a rate fy equals to 1 by fy uh, uh, fy, which is now here I said twice of fx, because I have upsampled by 2. Now here I have upsampled by I. That's why my fy is I of fx. That means your fy is greater than fx by a factor of I, by a factor of I. That means, so in upsample, the what you have to extract from the data is, from this representation is, or if you won't understand what I have done here, okay, I have inserted zeros in between, you can simply see these examples because starting only I said you have knowledge about your signals and systems. What I can say, you have an equation like y of n equals to x of 2n. One equation you take, x of n equals to y of n equals to x of 2n. Other equation you take, y1 of n equals to x of n by 2, x of n by 2. This is one problem you take, y of n equals to x of 2n. Other problem you take, y of n equals to x of n by 2. Means I can say you have seen the topic in the DSP first unit is time scaling. So what I have done here to make you understand how I drew the earlier figure is, your n equals to, first what is your problem, y of n equals to x into twice of n. Okay, other is x of n by 2, Now here this you see, because this is for downsampling, this is for upsampling. Here I am putting the values of n equals to 0 1 2 3 4. My x of n, what is my x of n is, now modified x of n is x of n by 2, and next will be my y of n. So what you can see here, 0 1 2 3 4 samples are there. Now when you put n equals to 0, x of 0 by 2 will be a 0, means x of 0, the output will be a 0, or the magnitude what they have given at 0, that will be present over here. But the suffix is what but the next input sample what you get is x of 0. Now when you put x of n equals to 1, when n equals to 1, that time 1 by 2, nothing but what, 0.5. That means at 0.5, here you have sample at 0, you have sample at 1. You don't have sample at 0.5, no? A magnitude at 0 was 1. Magnitude at 1 was 2. Now here you have inserted samples because you have done the time scaling equals, which is nothing but x of n by 2. N by 2 you have done. Because of that, what one zero got added in between these two samples, which magnitude is 0. Now same way, here also you can see where the same formula which I used, x of 1 by 2 nothing but 0.5. 0.5 पे your value was 0. So it was 0, but the value is 0.5. The same way you go on putting n equals to 2. 2 by 2 is 1. So at 1, x of 1. Now it is 3, let us say, n equals to 3. Then you will get 1.5. Means earlier you had only 0, 1, 2, 3, 4, so on. Now we are getting intermediate steps also, that is your 0.5, 1.5, 2.5, and so on. The same way you can go for x of 2n also. That is what I have done in this case. So what you have to collect from this upsampling. Upsampling is one of the method to convert sampling rate from one value to the another value. When you are having, let us say, input sampling rate as a 2 kilohertz, when you want to make it 4 kilohertz, you want to that means you are upsampling the input by a factor of 2. So you will do so. If your input is 2 and if it is output is your 8 kilohertz, you want to make it, definitely you have to make the upsampling by a factor of 4, and so on. Okay, so how you can achieve the upsampling is, we have to insert the samples, insert the zeros between two successive samples, and the number of samples which you have to insert depends upon the I minus 1, depends upon the value by which you are doing up or down sampling. Sorry, by which you want to upsample the data. Now same way you do downsampling even. So in that I can take the same example also, but I have taken different example. Earlier case in upsampling, what did I do? I have considered your fy is greater than your fx. In both the cases, what is my protocol? Definitely I'll be applying upsampling or downsampling when your fx is not equals to fy, when they are not same. Then only we'll go for multi-rate. Then only we can go for up or down sampling. So earlier I considered your output was greater. Now here I will consider my input is greater. My input is greater. What was my symbolic representation for my upsampling is this, the increased symbol, arrow up, going up by a factor. In case of decimal, arrow going downwards by the factor. Here again the same input, a discrete time input signal I am giving, f of x, discrete input time signal sampled at the rate of f of x, which is equals to 1 by tx. I am going to perform the down sampling. I have to reduce the rate, means I have a 10 kilohertz, I have to make it 5 kilohertz to it, and the outputs which I obtain is a different sampling rate which we desire to obtain, and that relation is this is less than this. Okay, now for that also same example, I will some sort of sequence again I will be going to take. Let x of n equals to 1 2 3 4 5 6 7, means n from 0 to 6 I have a sequence. I have taken different example than the previous. 0 to 6 are the samples. Now draw the same thing. Draw your graphical representation of this sequence, mathematical representation. You can draw something like this. You can draw something like 0, 1, 2, 3, 4, 5, 6. Okay, with some amplitude. Now what I have to do in earlier case, what I have done, upsampled. Upsampled means what? I was upsampling. And in terms of time, if I want to say, I have to reduce the time, and in terms of frequency, I have to increase the frequency of the given input. Now in case of downsampling, what I have to do? I have to exactly reverse of your upsampling. I was in case of upsampling, I was interested to reduce the sample, to make the sampler near and near, occur at repeatedly at a very short interval of time. In case of downsampling, what I am interested is I have to downsample. That means my output is less and my input is more. How I'll achieve that? I will go on increasing the distance between two. I'll increase the distance between two samples. This is what my Tx is. Earlier the Tx was the same like this. Then I was saying that I want less time duration between occurrence of the successive samples. So what did I do? I have inserted 0.5 also here, then 1.5, something like that. Here I have to expand. I have to expand the time interval. That means how I can do that? Definitely, when you want to have less time, we will compress the spectrum. We'll compress the spectrum. Whereas when you want to expand, definitely we will remove something. Like you have a group of 10 people, I want to widen up them. So simply, instead of placing them along or very long, simply I will remove some people, and I'll say that they got have they got separation and they got more distance between each other, something of that sort. Here in this also, I am saying that I want to increase the sampling rate. What I will do, I will do this time scaling, which is of something this form. That means here what I have done, I have I have starting from 0, that x of n equals to 0, whatever the magnitude is there, that I have written. Now earlier whatever I had drawn, simply take that down as it is. These are my old samples, old interval of time. That means n equals to 0 and 2, 3, 4, 5, 6. Because my inputs are starting from 0 and 6, ending to 6. The same thing I have copy pasted here, 0 to 6. But now the new interval of time at which this sample occurs, that you can see with I have wrote with orange pen, is n equals to 0, 1, 2, 3. Earlier you have from 0 to 6. Now my spectrum, now my input output sequence which I'll get is from 0 to 3 only. 0, 1, 2, 3. Only 4 samples. Earlier we have 3, 3, 6, 7 samples over there. Now we have reduced the number of samples. That means the unwanted one simply I have removed from my sequence. That is what we have done. How we can do just like that we are doing? No, definitely. You can see that this example. Y of n equals to x of 2 into n. Now you go on putting the value of n equals to from 0 to 6, no, n equals to input sequence 0 to sequence 0 to 6 you write down. I wrote till 4 only. 0, 1, 2, 3, 4. Like that you go on writing of n intervals from 0 to 6. Now what is your x of n? X of n is x of 2n now. X of 2n. X of 2n means that whatever the value of your n is there, you have to multiply it by 2, right? So you can see when it is n equals to 0, it becomes x of 0. So whatever the x of 0 value was there, x of 0 value was there, that will be writing as it is. That will be writing as it is. Now when n equals to 1, what happens? X of 2. X of 2. X of 2, you concentrate here. I'm saying x of 2. I'm not saying x of 1. I have kept the value of n equals to 1. I kept the value of n equals to 1. As I have multiplying by a factor of 2 over here, the next y of n will become x of 2. X of 2. Where is your x of 2? Is this. X of 0, x of 1, x of 2. X of 2. At x of 2, what is the value? That only will come. That means x of 1 will get removed. X of 1 will get removed. Same way you put n equals to 2 now. Definitely x of 4. So x of 4, x of n. N is 4. Sorry, and you kept 2, but you got x of 4. So what is your x of 4 value? Is over here. That means now you got this. So if in this way, if you put, what you observe is you get x of 0, x of 2, x of 4, x of 6, and so on. So the last sample in the input sequence, you got at 6, amplitude was 7, but that 7 magnitude same signal I got at n equals to 3 only, due to which because of this removing this sample, so first sample over here, second sample occurs at this time, which is the new n is your 1. That means definitely you have increased your sampling rate. Your ty got almost double. So because of that, your frequency will get vice versa of your ty. So in case of upsampling, how you have inserted the number of zeros, how many number of zeros you have inserted is your I minus 1, where I stands for interpolator. Where in this case, you are not inserting zeros, you are removing the samples. You are dropping the samples, and how you are dropping the samples between two successive samples. And how you are going to drop the samples, how many number of samples you are going to drop, that depends upon your the factor by which you are doing down sampling. That means by d minus 1. Same I minus 1 you have inserted 0, d minus 1 you have dropped the samples. If it is d equals to 2 now, 2 minus 1 by 1 samples you are going to remove. You have to drop 1 sample. If it is 3, then 3 minus 1 2. So 2 samples I will be removing. That means first sample is at 0. Next sample will be at 3 only. These 2 samples will get removed automatically. So new sequence which we get from this by applying this down sampling to it, we get is this n equals to 0, 1, 2, 3, and the magnitudes are 1, 3, 5, 7. So this is the representation of your decimation, sorry, down sampling I should say. So these are the two methods of doing sampling rate conversion from one to another, either by using down sampling or up sampling. Now this down sampling and up sampling, which and up sampling, now we'll call it as, we have to go for one more new term which is called as interpolation and decimation. Interpolation and decimation. Up sampling nothing but interpolation, and down sampling nothing but your decimation. So what difference you can see in this is, here you can see here your x of n is the input. This is the figure for interpolation now, and this is the mathematical representation of it. So this is by, you have to by heart the mathematical representation of interpolation, decimation, and I by d also. X of n, because you have lengthy derivations which is not at all required, that is they are not included in your syllabus. Here x of n, when this is input signal, when you are applying to this is upsampling. Here only one more new thing only you can see, that is your h of n. Here don't get confused with h of n. It is simply a low pass filter which we are using. This is a low pass filter which we are using at the output of your interpolation, so as to avoid the anti-imaging effect. In brief, you always remember this first thing, because there are very huge topics which we cannot do the mathematical analysis of it is, but you just definitely have to include this point when you are writing the theory about the interpolation and decimation. In case of upsampling, or the difference between upsampler and interpolation, we are going to pass the output obtained after upsampling to the low pass filter to avoid or to get anti-imaging effect. Anti-imaging effect means you don't want to replicate the images one after the another. You are sorting. Filter what it will does, what it will do, it will allow the certain band of frequency and rest it will not allow. That's it. So here in case of filter work is, for what purpose we are putting the low pass filter at the output of your interpolation is to avoid the anti-imaging effect. You don't want images to go on coming one after the other. We want only a certain pass band of frequencies, certain pass band of images which has to get passed in, rest should be rejected. So to avoid that, we are using the low pass filter at the output of your interpolation. Here input to the interpolation is your x of n, which is sampled at fx is equals to 1 by dx. Then it will get I of fx, which is allowed to pass through h of n through a low pass filter, which allows the unwanted frequency bands which are coming maybe get interrupted because of the surroundings, because of the another signals, which will get removed by this filter, and you will get the same signal, that is nothing but y of n equals to I into fx. So that means whatever the n values, the mathematical representation of this is x of n by I, when n so on. Otherwise, the downsampling, you will not have first block is your decimation, unlike your upsampling. Upsampling, interpolation, in which first interpolation divide first upsampling, then filter it out through low pass filter. Reverse will be happening in your downsampling. First you have to downsample. So first, what are the unwanted noises, unwanted signals are coming, that you are filtering out. So first is your filter, first is a low pass filter, followed by your decimation, followed by your downsampling, because you are not dealing with anti-imaging over here. Here you are going to avoid the aliasing effect. You don't want aliasing effect between two samples. So to avoid the aliasing effect means to have the anti-aliasing effect in this downsampler, we will first allow our input to the low pass filter so that all the unwanted signals will get rejected out and only the desired one will get passed to your decimation, so that the output obtained will be a fx by d, decimation fx by d. Here I into fx, here fx by d. So the difference between interpolation and decimation is you are increasing the sampling factor and then you are passing to low pass filter. In case of downsampling, in case of decimation, you are first filtering out the frequency components and then you are going to downsample it. So downsampling here, magnitude your pass band is your 1 for the limits 0 omega s from 0 to pi by d. Otherwise, it is 0. So they'll be giving heading in your exam and explain about interpolation and decimation. So first you have to start talk about upsampling, downsampling, and then interpolation and decimation. So only difference you can say is earlier I talked about this much only, this much only. In case of upsampling, in downsampling we talked about this. Now only you are allowing the signal to pass to the low pass filter. After and before that it gives as a interpolation and decimation factor. In case of interpolation, the filter is used to avoid the imaging effects, means anti-imaging effect we have to see in this interpolation. In case of downsampling, you don't want aliasing effect to be seen at the output, so we are going the filter what action it performs is anti-aliasing. Okay, so there's the two main important things one has to remember. Now till now, okay, 1 hour over. Okay. Actually, I have this much a little bit topic over here. This much one page.